Building upon my previous ESP32 IoT project, I created a wireless full-stack RGB light control system with an access point and web interface. Completed in September through October 2024, this RGB LED control software was originally intended as a scooter modification, but it can control many RGB LED systems using the proper wiring. This project demonstrates a deepened understanding and familiarity with ESP32 microcontrollers and embedded software development, while advancing my full-stack development capabilities. The system transforms the ESP32 into a standalone Wi-Fi hotspot, serving a web interface that allows users to customize RGB LED lighting through any browser-enabled device, seamlessly integrating hardware control through PWM with modern technologies like WebSockets and responsive design. For this build, the components needed goes as following: an ESP32 development board with Wi-Fi capability, 2 sets of common cathode RGB LEDs, with the left LED channels connected to GPIO 15 for red, 2 for green, and 4 for blue, and the right LED channels on GPIO 18 for red, 22 for green, and 23 for blue. You'll also need a micro USB cable for powering and serial debugging if you're going with the breadboard version of this project. And finally, you need any browser-enabled device like a phone, tablet, or PC to connect to the ESP32's Wi-Fi access point and navigate to its IP address to get the UI which controls the LED lighting. If you want to implement this project outside of a breadboard like I did with my scooter before it broke, it will also require a custom PCB design with a voltage regulator, matching the LED system you're trying to implement it to. This is just to make sure that the microcontroller gets the proper voltage. For instance, say they run at 12 volts, the microcontroller is not going to run at 12 volts, so you'll need to regulate the voltage to a voltage that the microcontroller can run at. You'll also need 6 MOSFETs, which stand for metal oxide semiconductor field effect transistors, to step up voltage to the LED output voltage. So say the microcontroller runs at 5 volt logic and the LEDs need 12 volts to run. That 5 volt signal can be sent through the MOSFET and then it'll relay it as a 12 volt signal to the LEDs. You also need precision soldering to create reliable electrical connections and integrate the system like I did inside of my scooter. Unfortunately, the scooter broke and I do not have the scooter with me anymore to demo, so I'll be using this breadboard setup, although you can still see all the functionality and how it would work inside of the scooter. The system architecture consists of 249 lines of C++ for the embedded backend and 592 lines of HTML, CSS, and JavaScript for the web interface. The ESP32 runs an async web server on port 80 to serve the web interface, alongside a WebSocket server on port 81 for real-time bidirectional communication between the front end and the back end. To conserve RAM, the entire HTML CSS interface is embedded into a programming memory string literal, storing the entire front end in flash memory rather than runtime RAM. When a user connects to the ESP32's access point and navigates to the IP address, they're presented with an interactive dashboard for LED control. The web interface allows users to select solid colors or create custom color sequences with independent control over left and right RGB LED channels. When users make selections, commands are sent over WebSocket using a lightweight custom protocol that includes main color, left color, and right color commands with embedded RGB values. The system uses Arduino JSON for JSON sequence deserialization with the ESP32's tight memory constraints. On the embedded side, a non-blocking timing loop handles color sequences while allowing concurrent WebSocket event handling. Once those events are handled, PWM signals drive the RGB LEDs controlling the color based off what the user inputted on the front end. So this is a breadboard and how everything's wired up. Connect the micro USB to get power to it, and then you take any browser enabled device. I'm just going to use my iPhone, although you can use a computer, you can use anything that has a browser, really. To go into Wi-Fi, now already connected, so you just connect to the Wi-Fi. Should say scooter mod. This is just the SSID in the program. You can change it to be whatever. It could literally be your name, it could be anything, but I just have it as scooter mod because that's what it was originally used for. And then you go into the browser on your browser enabled device, you type in the IP address, which is 192.168.4.1. That'll take you to the front end that it's displaying, and from here you can control it. Now I'm gonna turn the light off. From here you can control it. So if I go into color, this is just the main color. So say I go into color, and then this is the main color. So this changes the color for both of the LEDs. As you can see, this is the right one, and then this is the left one. Change the color for both of them. It has multiple adjustments. Change the color to literally any RGB color.
And yeah. And as you can see, the color that you set it to also matches the UI. So when it's purple, it's purple. When it's red, it's red. It's just a little nice touch that I added. And then say I exit out the main color page by clicking this back button. You go into mode, and then you have two options. You can either control the light side or the sequences. Now I'm gonna do the light side first. So basically, this just controls the light side. So say I set one side to red, and then I set the right side to green. So the left side is set to red, and the right side is set to green. As you can see, it matches. And once again, you can do this with basically any color, any RGB color, and it'll also match the side to the color. While the left is green and the right is blue, the left LED will match the left side of your screen, same with the right and the right side. Which is, once again, a nice touch. And then this also stays, and then say you went back into main mode when you switched it, and then it'll just adjust back to full screen. And now this is also another cool thing. You can add light sequences. So say I want it to flash red and then off, I can add the color red. You can choose how long you want it to as a delay in milliseconds. So 1,000 milliseconds is 1 second. So say I want it on red for 1 second, I'll add that, and then you can see what you have, like what sequence is gonna play. And then say I want it to go off for the other time, so I'll set it to black, and then I'll add. So you can see it's gonna be red for 1 second, and then it's gonna be black for 1 second. So now you see on, off, on, off, on, off, on, off. And this also will sync up, so it's pretty cool. You can also add more than 2. You can basically have infinite sequences in here. So say I want it to be black for 2 seconds or off for 2 seconds. Then I could stop, play it again. It'll be on for 1, off for 2, on for 1, off for 2. And then say I want it to just be red. You can also just set the sequence to be red indefinitely, and this will just loop through red. And like I said, this can also be any color. So I could set it to blue, and then it'll do 1 second red, 1 second blue, and you can also customize the time. So now it's switching between red and blue, and you can do this with any color. You can add as many colors as you want inside of the sequence, and you can just stop the sequence by clicking the stop button. It'll stop on whatever color it was at last. You can go back and then adjust it main color as normal. So yeah, that's pretty much it.
Now I'm gonna make this code review really quick because in my last few videos, it's been like the majority of the video and I've been going through line by line. So I'm just gonna give you a basic overview. In this index.h, this is where we put the HTML document into a string literal. That's a pointer of HTML content, which we then reference later inside of this the C++ backend. But this basically is just the full front end, as you can see here. It's a HTML, and then add some CSS to style it. That basically just makes it look how you guys saw it look when I just did the demo. This is actual HTML, or like the templating for the website. You can see the color side, blah blah blah. And then this is the JavaScript. This sets up the WebSocket. These are just variables. Most of it is just selecting elements from the DOM. These are our functions, and then we call these functions on events. So see, we have event listeners, and then we call the functions that we just made on those events. And then we have, this is like the sequence event listener. This is the actual backend. These basically just include our libraries. These are the pens that I went over earlier on which the LED rests. This is the SSID and the password for the Wi-Fi access point. This basically just like keeps timing of the loop. And this is the JSON doc that contains like the sequence that the loop comes in. These are just some functions. This serves the HTML, just change the red color, change blue, blah, 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 blah. This handles the main color. This handles the left color. This handles the right color. As you can see, the functions are very self-explanatory. Like the line by line isn't really needed. This converts a hex value to RGB. So it basically gets a hex value and then it converts it into red, green, and blue values. This is for handling WebSocket events. And if it handles, then blah, blah, blah. Handle left, handle right. So you see main color, left color, and right color as I went over earlier. These are the main cases that we handle. And then this is for handling the sequences. So this is the setup where we set everything up. We set all the pins to output because we're going to output PWM. We start the Wi-Fi, we begin the WebSocket, and we serve the HTML, and we're 80. And this is the loop that just runs continuously where we are basically just constantly checking the WebSocket. And then if the sequence loop is true, then that means that we have a sequence running. And then we run this, basically get the JSON doc, and then we loop through it as an array, and each item, blah, 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 color, blah, blah, blah. Then we write it here. And then we iterate the index, so we just keep moving through the loop. And that's basically it for the code. This project presented several significant technical challenges. Embedding a full HTML, CSS, JavaScript interface into a program memory string literal without runtime RAM overhead required careful memory management. Setting up an async web server on port 80 alongside a web server on port 81 also demanded precise configuration. I designed a lightweight custom protocol for color commands and parsing embedded RGB values, whilst integrating Arduino JSON for JSON sequence deserialization within tight memory constraints. Implementing a non-blocking timing loop for color sequences that allow concurrent WebSocket event handling was crucial for maintaining real-time responsiveness. Through this project, I demonstrated a wide range of skills. PCB design for creating custom circuit board layouts, precision soldering to bring the design circuits to life and integrate them with the scooter, full stack IoT development integrating front end with embedded backend, advanced use of WebSockets for low latency UI to device communication, memory efficient storage of large HTML assets in flash memory, JSON parsing and dynamic command handling on resource constrained hardware, PWM LED driving and color mixing across multiple channels, non-blocking event loops and state machine design for real-time sequence playback, ESP32 soft access point configuration for standalone Wi-Fi hotspot functionality, custom command protocol and state machine implementation for synchronized color sequences, as well as performance optimization for resource constrained environments. This scooter LED modification project represents a crucial stepping stone in my development journey as an embedded systems engineer and full stack developer, demonstrating my ability to create seamless integrations between hardware control and modern web interfaces. The skills developed here, WebSocket communication, memory efficient embedded web servers, real-time pulse width modulation control, and custom PCB design laid the groundwork for my next major project, a full stack ESP32 based quadcopter flight controller with real-time PID tuning and comprehensive telemetry visualization. That project, completed in July of 2025, would take these foundational concepts to the next level,